Okay. Okay, we have just winner and Ezelikai in the class today. So I'm about to share my screen. Can you see my screen? Hello? Winner, can you see my screen? Can anyone see my screen?
Yes.
Okay. So today we'll be learning about periodicity in chemistry, the topic we were supposed to learn the first week. Okay. And these are the items that we'll be learning for today. We'll be learning about the periodic table, trends in the periodic table, about electronic configuration, periodic properties and their definition. We would also be learning about some special elements. Now, each of these topics are gotten from your YX syllabus. I don't like that this thing is echoing. Okay, we'll also be learning about reactions between acids, metals, their oxides, and also carbonates. And we'll also learn about alkali metals, um, some periodic gradation of some elements, and about transition metals. So hopefully we're able to exhaust all of these things before the end of this class by 8:30. Okay, so we have a periodic table here. I don't know if you can see the table. If it's visible enough to you, let me let me know. Is everyone able to see this periodic table? Okay. So now let's first talk about what we know about a periodic table. Okay. First of all, there have been different developments about the periodic table from the time of its discovery. Okay, so at first, the periodic table has not always been arranged in this format, the way you can see it on the screen. Okay, there have been an arrangement from one scientist to the other, but this one you can see on the screen is the most recent one. Okay, That's why it is being called the modern periodic table. Melody, you're welcome. That's why it's being called the modern periodic table. At first, the periodic table was arranged in a way of it's being called the triads, okay, where you can relate one element to the other based on their average atomic mass. Okay, so as time went on, the periodic table was now also arranged in terms of their atomic mass, where elements of the same properties are arranged in the same group. Even before then, periodic table was arranged putting in focus the group 18 elements. The elements I said in the last class that are the stable elements, okay, which are the last elements involving helium, neon, argon, krypton, the last group, okay. But then the modern periodic table arranges the periodic table in terms of increasing atomic number. Okay, that means from 1, 2, 3, 4, and the rest of it in such manner that every, and also in groups and columns, such way that every member of the same group, which is a column from top to bottom, okay, are having the same chemical properties. And so they will act the same way. So that is like um, a brief introduction of what a periodic table is all about. Okay, so like I said, the periodic table is arranged in groups and in columns. The groups are from top to bottom. Let me share another screen because this one would not. Melody, I wanted to um, correct something we did in the last class. So please excuse me. When we're talking about dichromates, okay, the CR2 O7 that you asked me about when we talk about what the bond was. Do you remember? Melody. Hello, is Melody there?
Yes, ma. Yes, ma.
Okay.
Please, what did
So
you
that
say?
that's
Repeat the
that was
question.
the last question. The question you asked the last time about
Yes, ma.
the bond that exists between CR2O7 dichromate,
Yes.
and concluded is ionic.
Yes, ma.
So the bond that actually exists in that molecule isn't ionic, but it's covalent. And I'm going to explain it now. Let me share the other screen. Okay, so we have this, right? Now these ones are bonded together by covalent bond. Okay, this was a question Melody asked in the last class. Okay, but when these one now is bonded with something like potassium, a positive ion. These whole thing, they are already negative. It's already together a negative ion. When it is bonded together with something like potassium, okay, that's when we have something like potassium dichromate. That would now be ionic bond, because this is the positive end and this is the negative end. Okay, so but the bond that combines this chromium and this oxygen is covalent. Okay, Melody. So now let's look at this periodic table again. So like I said, groups are the columns. Columns is from top to bottom. What would ordinary call row? So from this top of this one going down is a column, okay, and not a row. So the column is what makes the group in the periodic table. So we can say from top to bottom is the group, then from left to right is the period. Okay, so this 1, 2, 3, 4, 5, 6 that I'm writing with black pen are all the groups, and the period would be the one I'm writing with red pen. Okay, so if you're being asked what are some elements in group 2, would say all the elements we see from top to bottom under 2. So which is beryllium, magnesium, calcium, strontium, okay. But if we're being asked what are some elements in period 2, magnesium is not an element in period 2. It will be all the elements in this number 2 from left to right. So it will be lithium, beryllium, boron, carbon, okay. So in essence, all the elements in period 1 are only hydrogen and helium. Those are the only two elements in period 1. Okay, so we have introduced that about the periodic table, and we said based on the modern periodic table, every member of the same group share the same properties, so they can be prepared in the same way, they carry out the same reaction. So if hydrogen is going to react with or rather if sodium is going to react with oxygen, okay, to give us a basic oxide, it means potassium is going to carry out the same process. It's also going to give us the same product, a basic oxide. It means every member of that group would do likewise. Okay. The same thing for group 2. If one member of the group does something and give a particular product or it acts a particular way, the other members of the group will act that way. That's what chemical property is all about. So it's more like a member of a members of a family that do things alike. Okay, so the next thing we are going to be going into is uh, electronic configuration. Now, for us to understand electronic configuration, we also have to understand the periodic table, understand certain things. Now, there are two ways we can write electronic configuration. Okay, we must have been taught. Have you all heard about this method of electronic configuration? Have you seen something like this? When maybe in your textbook or in class you see something like 1s square, 2p square. Have you seen something like this? And it's called the ALF. Okay, Melody has. Who else? We should have Mohammed. And this Eze Leke. Okay, I would just call you Eze because I'm not sure how to pronounce this your name. And winners. So the three of you, you're familiar with this method, right? Just give a thumbs up if you are, just as Melody did. If you're not familiar with it, you give a thumbs down. Okay. Okay,
Yes.
so like I said, there are two ways we can write electronic configuration. Okay. The first way is the electron shell method. Okay, we can call that the Bohr method. I hope you all can still see my screen. Okay,
Yes.
Bohr's method. Now the other way is the Aufbau method. Now this Bohr method is that one that you see one circle and you see some circles inside, you see another circle and you see another circle, you see circles inside. This is the Bohr method. It's a very common method and it's very useful for the first 20 elements. But when when we are dealing more than elements that are greater than the first 20, when we have entered 21, we have about 118 elements in the periodic table. So when we have gone past 20, it is this Aufbau method that is often used because it's more like a more reliable method than the Bohr's method. The Bohr's method is reliable, but it's mostly reliable for the first 20 elements. Now, the Aufbau method is where you do that 1s squared, 2s squared, and things like that. So I will show you how to do each of them. Now, for the electron shell method, the things we have to put in mind is that we have what is called energy level. Okay. Let us say this is an atom. This is the typical structure of an atom you were being taught. We said an atom inside of it is made of proton and neutron, and outside of it are electrons moving around it. So this is how where we got the Bohr's method of electronic configuration from. So the Bohr's method is telling us that these circles around where the nucleus is, this inner circle is the nucleus. Now the circles around the nucleus, there are more than one of them. These circles are called energy levels. So when we are drawing electronic configuration, we are drawing the electrons moving around these electron energy levels rather. Okay, so for example, if we have an element like oxygen, okay, oxygen has an atomic number of 8. Okay, this means that for a neutral oxygen, when we say neutral oxygen, we mean just O. It's not charged. It's not having any -2, minus anything, or plus anything. For a neutral oxygen, the the atomic number is 8, which also implies that the electron number would also be 8. So when we are drawing the electronic configuration there means we are dealing with electrons, right? So the electronic configuration would be we are drawing the 8 electrons of oxygen. So we want to do that according to Bohr. The first energy level, remember I said this circle here is called energy level. Okay, and this dot here, these are the electrons. It represents electrons. So based on Bohr, the first energy level, which is the one closest to the nucleus, has a maximum. It should be more than this, maximum of 2 electrons. While the second energy level has a maximum of 8 electrons. Okay, there's actually a formula to get this. Okay, and the third one has a maximum of 18. But for the first 20 elements, we would continue with 8 and 8 and so on, okay? And also for your level. So as we are progressing in energy level, we keep having a maximum of 8 electrons. Okay, I can see someone raising up their hand. Do you have a question? Okay. So now, if we are to draw for oxygen, for example, the first energy level, we have 2 electrons, maximum of 2, like we said. If we are drawing the electronic configuration of oxygen, it means that all the electrons we'll be drawing should be 8 altogether. So we have written out 2. So we cannot fill any more electron in this first energy level. Now we'll draw the second energy level. We said the second energy level has a maximum of 8. The first one has maximum of 2. So the second one will have a maximum of 8. So we have to draw out the 8. 1, 2, 3, 4, 5, 6, 7, 8. But if we do that, that means we're having 10 electrons here. But oxygen should have 8 electrons, not 10. Okay, so that means we are going to be removing 2 of the electrons. Okay, so let us remove. Oh, we will remove 2 of the electrons. Oh, I have mistakenly. Okay, so we're going to remove 2 of the electrons. So we're going to. Okay, so this will now be 2, 6. Together, it will give us 8. Are you seeing it? So at the end of the day, you should focus on how many electrons a particular element should have. Okay, so that means the electronic configuration of oxygen is 2, 6. 2 plus 6 is 8, and 8 is the atomic number for oxygen. Okay, now the next question is, okay, the next one is for Auf-Bauf method. Auf-Bauf method is like this. Now this is how it is arranged. A simple way to just put it for you guys. You will first write 1, 2, 3, 4, 5. Then 2, 3, 4, 5. 3, 4, 5. 4, 5. Now our valve method is based off subshells. Okay, now we have 4 subshells, which is the S, the P, the D, and the F. Okay, now the S subshell has a maximum of 2 electrons. These are things you have to more like memorize. It's not difficult, okay? Just know them. Although there are also formulas to know these numbers, okay? But you don't have to use the formula if it's just a fixed number, right? So the P subshell has a maximum of 6 electrons, the D has a maximum of 10, and F has a maximum of 14. Now, if you notice, they are increasing by 4, right? The difference between them is a 4. Now, if we want to, the Auf-Bauf model is this 1, 2, 3, 4, 5, 2, 3, 4, 5, 3, 4, 5, 4, 5. Now, we write each of them is S. For this 1, 2, 3, 4, 5, they all belongs to the S subshell. The next one is P subshell, D subshell, and F subshell. Okay, so if we want to now write the electronic configuration of, let me say, sodium is 11 using the Auf-Bauf method. This is what we'll do. Auf-Bauf is that we are going in a diagonal direction. That is to say something like this, from top to bottom. Okay, so we'll be writing it like, we'll start from 1S, we'll now do 2S. So it's more like writing this kind of line. So the first shell that will come is 1S, then next to 2S, next to 2P before 3S, because you are coming from this top to this bottom. Okay, then 3S, then the next one that will come is 3P, 4S, 3P, 4S, right? That's the trend. Who can tell me what will come next after 4S?
Theory D.
3D, very good. And then 4P, right? Then 5S. That's the trend. Now, How are we writing these are just the subshell, okay? Each the one there, um, let me show you people there. Are you seeing this? Now, this is okay. Don't worry about that. Okay, now to draw the electronic configuration of this one here is not what is telling you the electrons. Okay, that's energy level. Now the S there is telling you the subshell, right? Now the number of electron is going to be the power that each of them is having. Remember we said S has a maximum of 2 electrons. So give the 2 to this S. This is 2S. We're still dealing with S. So we're having maximum of 2 electrons. This is 2P. Now we're dealing with P. So it will have maximum of 6 electrons. How many electrons do we now have? We now have 2, 4. 4 plus 6 is 10. So we're actually counting the powers, okay, the rest of power. These 2, 4, 6, these are the electrons. Now the next is 3s. S there tells you how many electrons you should have, maximum of 2, right? But we are drawing for sodium, and sodium is 11. So since we've gotten 10 from 2 to 6, what is left is 1. So this is the configuration for sodium: 1s square, 2s square, 2p6, 2s1. Okay, so how do we get this 1s, 2s, 2p? Is by this model, this diagram here that I just drew. Okay, so it's actually not difficult. Now, based on this, so by the end of this class, okay, I want you people to write the configuration of calcium, and also of sulfur. Calcium is 20, sulfur is 16. Okay, so you people will work on this using the Auf method. That will be at the end of the class. But for now, let us go. And so the 3, 4 of you should write this in your notes. Then you tell me your answers by towards the end of the class when we are doing some practice questions. Now, I believe, do you all understand what we have just done? Mm? All right, I can see the thumbs up. Now, the next thing we are going to be talking about is we'll be talking about, let me see. We'll be talking about trends in the periodic table. Okay. So the periodic table, when we talk about trends there, okay, we'll talk about what is happening in each group and in each period of the periodic table. By the way, before we go there, based on what we have looked at in the Auf principle, group 1 and group 2, their electronic configuration always ends with a S. Just as we did with sodium now, it ends in what? A 3s, right? So it will end with a S. So we can now say that group 1 and 2 are the S block. Okay, then this group of non-metals are the D block. I'm sorry, the P block. Then transition metals at the middle are the D block. That means their electronic configuration will usually end with a D. We are using a Hubbard method. And these ones at the bottom, lactanides and actinides, are the F block. Okay, just as we can see it here. Okay. Now we said we'll be looking at trends in the periodic table. The first trend is atomic size. Okay, atomic size. These are things you should know. Now, across the group, atomic size would decrease. Okay, why is it decreasing? Or what do we even know about atomic size? If we're going from left to right, for example, we have across the period. Let us say we are dealing with period 1, for example. Period 1 include hydrogen and helium alone. Period 2 includes sodium, also magnesium, aluminium. These are the people in period 2. Okay, so we are saying now from sodium to aluminium to the end of that period, atomic size is decreasing. So if we are writing the electron configuration of sodium, for example, okay, we are having something like this. This is actually period 3, not period 2. Okay, we are having something like this. We have our 8 electron here. And, okay, just one in the last one. And for magnesium, okay, we're also still going to have 3 shells. Okay, just that the last one is going to have 2 electrons in it, unlike sodium that have only 1 electron. Now, aluminium, we're also going to have 3 shells. Okay, just that it's going to have 3 electrons in it, unlike magnesium. So all of them have the same number of shells. Okay, now why is it now decreasing? Their number of shell is the same number, but because of the um, number of proton that is increasing, so their potential charge is increasing, and so electrons are pulled closer and closer to the what is it called? To the nucleus, which is the inner part. Okay, so that is what happens there. But when we talk about down the group, atomic um size would increase. It makes sense that it would increase because in group 1, for example, we have hydrogen first, and the shape of hydrogen, so to say, is going to be just this. Then lithium is the next member of group 1. That is down the group, it's increasing. Sodium is the next member. Lithium is going to be like this. 3. While sodium is going to be like this, 1, 2, 3. So it makes more sense because we're adding more shells, and so the size is increasing down the group. Now, in terms of ionic size, positive ions are smaller than their atoms. So we don't really are smaller than their atom because it makes sense because they are donating, right? So, for example, sodium ion is usually sodium plus. That means it has lost 1 electron. Okay, so that is to say it's no longer 11, it's now 10 electrons. So it will now be smaller than how it used to be, which is 11, right? While negative ions, anions, they are acceptors. They've already accepted, so they are more than they used to be. So in terms of ionization energy is the energy required to remove an electron from an atom. So first ionization energy are usually easier, okay, and requires less energy than second ionization energy and than third ionization energy. Okay. So across the period, ionization energy increases, while down a group, it decreases. Okay. Now, electron affinity is the tendency or ability of an element to be able to attract electrons. Okay, so electron affinity would increase across a period because this side of the periodic table, we have something like sodium, for example. I like using sodium because it's the first group one element that comes to mind. Okay, let's say potassium. But when you're going across the period, we meet somebody like chlorine. Okay, now electron affinity there. Affinity means attracting something to yourself, right? So electron affinity means an element being able to attract electron to himself, to gain electron. And would agree that in the periodic table, the people that gain electrons are the non-metals, people like chlorine, and the people at the right side. Okay, this is the right side, this side. Okay, now, so that is, and metals rather are the people that donate. So they don't attract electron. Instead, they tend to give off, while non-metals are the ones that attract electrons, and so that's why they will be accepting. That's why they will not acquire negative charge. Okay, so that is why electron affinity would will increase as you go across the period, and it will decrease down the group. Okay, now the next one is electronegativity. This one is very relatable because the right hand side of the periodic table, which are the non-metals, they are the people that are negative. So it's almost like the same thing with electron affinity. So those people, as you go across the period, the element tends to be more electronegative, and so electronegativity would increase. So this picture here, this old diagram and the old PDF I'm using is from a helpful WIEC platform where people go to practice WIEC and some examinations. It's called Brains Academy. So this particular table helps to brief everything that has gone, that we have talked about rather. Okay, people that are increasing across the group, decreasing, so you can have a table for yourself. Okay, how you can analyze what is going on from left to right in terms of electronegativity, electron affinity, ionization energy, nuclear charge, metallic character, okay, atomic size. In terms of all these, what is happening across the group or down the period. So you might be asked something like this in your examination, okay? We have something like sodium, then let's say we have boron, let's say we have calcium, let's say we have sulfur and oxygen, and they tell you to arrange this in terms of increasing electronegativity. So someone should tell me which is going to be the most electronegative here in terms of increasing electronegativity.
Oxygen.
Oxygen, very good. So who is going to be next to oxygen? We have a periodic table here in case you want to see it. Look at our periodic tables. Look at where oxygen is. Then sulfur, where is sulfur? Look at where sulfur is. Okay. Then we also have which other one is there? Boron. Boron in group 13 and sodium. So what's her name? Melody has told us one. Winner. What's the next one after oxygen? Sulfur, very
Sulfur.
good. If we notice, sulfur and oxygen are both in the same group. Okay. So why is oxygen more electronegative than sulfur? When we talked about the trend in electronegativity, we said what? It increases across the period and decreases down the group. Okay, so that is why oxygen is more electronegative than sulfur. Okay, but across the period means from lithium, okay, let me zoom it in. From lithium to where this oxygen fluorine is, it is increasing. Okay, while from oxygen down, it is now decreasing, which make oxygen the highest, and the one at the bottom is the lowest. So sulfur, yes, after sulfur, who is coming next? That is sulfur less than oxygen. Oxygen is the oga pata in this case. Who else is in this call? Let me check. Osenwenkai or Eze.
Oh,
You said? Am I not pronouncing it well? Ose. Let me call you that instead. Because I know that's the short form of your name. Ose, what is the next one in this trend? We've already written out oxygen. We've already written out sulfur. So who is going to follow? Yes.
calcium.
Is what?
Calcium.
Calcium. Who is answering calcium? Winner.
Ma.
So that is to say calcium is the next electronegative.
Yes.
No. Melody, is that true? You tried. Thanks for the efforts. But it's not calcium.
No, 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 no.
Calcium is at the left side. Let me show you the periodic table. Now, the remaining ones for us to match is sodium, boron, and calcium. See where calcium is. Let me circle calcium for you. You see where calcium is. See where sodium is. See where boron is. And we said that as you are going like this, the electronegativity is increasing. So that is to say, all the ones in this side, in this right-hand side, are more electronegative than the people in the
What is
left.
that?
So which one is the next? Which one is, we said oxygen is the most negative, right? Then before sulfur. Then which one is the one following
Boron.
sulfur? Boron. That's very good. Who said boron? Who said the boron? Melody. Okay. Now after boron, that means we've already answered for boron. Boron is the next. After boron, which one should follow? I want Winner to answer this one. Winner, do you get the gist now? The more you are towards the left, the less negative you are. In fact, the more positive you are. So you are contradicting being negative. So between sodium and calcium, which one is more going to act negative than the other?
So
Yeah, did you say something?
look like so
It looked like sodium. Okay, I can see the chat. Ose is the principal. Sorry, ma. Oh, sir. I was thinking you're one of the students. You're welcome. Um, yes, winner. Winner, which of them? You said it's sodium. It's like you're guessing. You said what?
repeat the question
I
again.
mean, okay.
I can repeat the question.
The question is between sodium and calcium, which one is more electronegative? Let me put it like that. We're doing a trend here. We are giving a question now. They said we have sodium, boron, I've actually seen a question like this in your exam. We have sodium, boron, calcium, sulfur, oxygen. Okay. Then calcium.
Calcium.
Calcium is the next one. So they were now asking you to write it in increasing electronegativity. Means that they're asking you to write from the least negative to the most negative. So the most negative is the one you will write last or at the end. The least negative is sodium because sodium is at the other extreme end. You can see it's at the positive people side. Like I told you, in the periodic table, group 1 and 2 are very most positive. So we have sodium, then calcium, then boron, and then sulfur before our oxygen. Then we will now write negative less than sign because sodium is less than this in terms of negativity, less than the boron, less than sulfur, and less than oxygen, which make oxygen the ultimate in this case. Okay, the same thing if we are given something like fluorine. We are giving fluorine, chlorine, bromine, all of them are in group 17. They now ask you which is the most electronegative. It's fluorine because we said electronegativity decreases down the group. So the one at the top is the ultimate. Okay. But if they say between fluorine and oxygen, let me zoom in this periodic table. It is fluorine still that is the most because it decreases from left to right across the period. Increases rather from left to right across the period. So just know the trend. So when you're giving list of elements, you would know which is greater, which is least. Okay. Now the next thing, I hope everyone understand or understood this aspect. Now the next thing we are going to be learning. Okay, what if we have, let me give another example. What if we have something like, we have this now. We have aluminium, phosphorus, beryllium, calcium, nitrogen, oxygen. And we want you to arrange this in increasing atomic size. Okay, we know that in terms of atomic size increases no or let me write it here, decreases from left to right, and it increases from top to bottom. That is in group. Left to right in period. Okay, so who can give us this one? Arrange it in increasing atomic size. You should have a periodic table. Let me just draw a quick periodic table for you here. We have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, then our helium at the top, neon, again, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. So tell me, let me know, which is going to be the most, in terms of increasing electron affinity? Yes. Based on this, okay, we can see that we said electron affinity, atomic size is what I said. Atomic size decreases across a period, okay, and we can see now, and increases down a group. So across this period, where do we find aluminium? We find aluminium here, then we see where phosphorus is, then we see where beryllium is, and then calcium. So between beryllium and calcium, you see both of them are in the same group, okay? But we agree that calcium will have a greater size than beryllium. So since we have seen the relationship between those two, we see that beryllium is less than calcium, okay? So we have written out the relationship between these two. Now we see nitrogen and phosphorus are in the same group. We also know that phosphorus has a higher size than nitrogen, okay? But in terms of beryllium and calcium, how are we going to write it? Across a period, it is decreasing, okay? So that means the atomic size of nitrogen and phosphorus are going to be less than that of beryllium and calcium. And then oxygen. You see, oxygen is here. It's decreasing across the period. Okay, so that is to say, oxygen is going to be less than all these ones in that period. So oxygen will be here. And then aluminium. Aluminium is beneath boron. Okay, so aluminium will be less than aluminium will be greater than nitrogen, okay, also greater than oxygen. So all the ones at the top of aluminium, it will be greater than them all. So we are only comparing aluminium now with phosphorus and with Aluminium with phosphorus and also with calcium. Now, aluminium will be greater in size than phosphorus because it is decreasing across the period. Let me rewrite this. But will aluminium be greater in size than what is it called? Nitrogen? Yes. And it will also be greater than oxygen. So aluminium will be somewhere further here. So we have something like this. Do we all understand? So this thing is more like logic and common sense. Like it's more like analyzing the whole thing. Okay? Is anybody confused? If you are confused, let me see it in the chat that you are confused. Please, I'm using the wrong sign. This should be less than. Less than this, less than this, less than this, okay? So properly writing this, we're going to have less than beryllium, less than phosphorus, less than aluminium, less than calcium. Okay? Can you all see my screen? Okay, so this will now be the trend in terms of electron, in terms of atomic size rather. Now let us move on to the next thing we have. Okay, which is some reactions between reactions in metals. Okay, now for metals, acids, this thing it often comes out in your WAEC, so please pay attention to some of these reactions. Acids, okay, will react, metals will react with acid to give us salt and hydrogen gas. We know neutralization reaction, right? Where acid reacts with base to give us salt and water. Now, when it is just metal, the acid is reacting with, okay, the metals include group 1 and group 2 elements. So we are dealing with reactions of group 1 and 2 elements. It gives us salt and hydrogen gas. So we can see an example of that process on the screen. Now also metal oxides are basic oxides. So we also talk about that when we're talking about metals. So a basic oxide acts as base. Sorry, metal oxides act as base. Okay. So sodium oxide, magnesium oxide, aluminum oxide, all these are metal oxides and they will act as a base. While non-metal oxides, okay, for example, sulfur oxide, okay, all these are acidic oxides. Okay, so group 1 elements are called alkali metals. Okay, they are the first column of the periodic table, they are very metallic and react, they will form base when they react with water. Okay, so these are two things. Metals would react with acid to form salt and hydrogen. Metals will react with base to form metals would react with base, yeah, to form metals will react with water to form base. Okay, metals will react, so these are two reactions of metals. Metals will react with water to form base, which is the basic oxide. Metal will react with acid to form salt and hydrogen gas. So you can be given a question, for example, what would happen if um if for example, or write an equation for the reaction between sodium oxide. They'll write it like this. They won't tell you what's the formula for sodium oxide. Between sodium oxide and hydrochloric acid. You already know that metal oxides, which is sodium now is the metal plus oxygen oxide. Metal oxide are bases. So when base reacts with acid, it gives you what? Salt and water. So you already know that this is what you are going to do. Sodium oxide is this. Then hydrochloric acid, you get your what? Your salt plus your water. You balance it. Now what if they ask you, write a balanced equation for the reaction between um magnesium and water, or when magnesium dissolve in water, what do we get? They expect you to already know that magnesium is a metal and it is water. So when metal and water react, it will always give you a base. So they expect that you already know. So the metal mustn't be magnesium. It can be any other element in group 1 and 2 of the periodic table. So provided you know the product that will be formed, you will know that you will form a metal oxide. Like magnesium oxide now is a metal oxide, and this is the formula, then plus your hydrogen. So if this reaction would properly be written like this: metal plus H2O to give you metal oxide plus hydrogen gas. Okay, also metal will also react with acid to give us what? Salt plus hydrogen gas. So these are reactions of metal. This metal can be any other metal in the periodic table. They can ask you for sodium, for calcium, for potassium, for aluminium. Okay. Now, okay, what other thing? Now these are some physical properties of metals in group 1 element. Okay, they are soft. They have low density. Okay, that is they are more lighter than water. Now, they are good conductors of heat and electricity because they are metals, right? Now they have slippery appearance. When we talk about physical properties in chemistry, we talk about those properties you can see, feel, touch, smell. Okay, while chemical properties are those properties. When we talk about chemical properties, we are talking about all the reactions that element or that group carry out. Okay, reactions with oxygen, reactions with water, reactions with this, reaction with that. That is what chemical properties is all about. Chemical properties is not asking you the boiling point, it's not asking you the melting point, it's not asking you those other things. They're asking you the equations, the reactions. Okay, now for group 1 element, they are very reactive. because they have that one electron they always like to give up. So they will have to always want to react with another element, usually non-metal, so that they will become stable. Now they react with oxygen to give metal oxide, which are basic oxide. They also react with water to give us bases. They react with halogens to give us salt. So these are some reactions of metal oxides. Okay. Okay, sorry about that. Earlier in the call, I gave you two elements to write the electronic configuration using the Auerbach method. I think it's calcium and aluminium. So can you all, those of you that were in the class, can you tell me what your answers are? Auerbach method. Yes, I'm waiting. Yes, I'm waiting. I want to see your answers. You can also write it down in the chat. That of calcium and aluminium using the Auerbach method. No, don't tell me by electron shell method. So I'm giving you all like 2 more minutes to give that answer to the question. You can start attempting it in your notebook, and then you tell me what you got. Melody, what did you get? And the rest of you, oh, we have only Melody and Winner now. So what was your answer? The electronic configuration of calcium using the Auerbach method. I want to see your answers.
For calcium, for calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2.
Very good. Well done. I'm glad you are in fact you are a smart kid. Winners. So you tell me for aluminium. Yes, Melody, you're raising up your hand.
I wanted to say for sulfur.
Okay, it was sulfur I gave you the other time, right? Okay, you can say for sulfur.
No,
The
no.
winners will tell us for aluminium.
Okay. For sulfur is 1s2, 2s2, 2p6, 3s2, 3p4.
Very, very good. That is it. When you count all the electrons together, it's giving you 16. So winners, as we are waiting for your own, let me ask a question. Based on what we have learned now, tell me two chemical properties of um alkali metals, group 1 elements. Two chemical properties. Yes, Melody.
Reaction with water.
Very good. When they react with water, metal now, when they react with water, what are you expecting to get?
Metal oxides and hydrogen gas.
Very good. It gives you metal. Metal oxides are what? Are they acid or base?
It, it,
They are what? Very good. They
it,
are base. Yes. Now what if metals now react with oxygen? What would they give you? Yes, what will you get if metals react with oxygen? Yes, Melody or winner. It will give you what?
it
When
acid.
metals react with oxygen, I didn't get you. When metals react with oxygen, they give you metal oxides, which are still base. Okay? Now, what if metals react with acids? What would you get? Yes, winners. Winner, we will be coming back to you. That aluminium, you will answer it. When metal, Melody, can you hear me? Melody,
Yes, ma'am.
can you hear me?
Yes, ma'am.
I said when metals react with acid, what would you get?
We form salt and water.
Yeah, you tried very well. But we will form salt and hydrogen gas. Okay? Because there's no oxygen there to be making us form water. We know there's oxygen in water. So we'll just form the H2. There is no O. So when metal reacts with acid, will form salt and hydrogen gas. When metal reacts with oxygen, will form metal oxide. When they react with chlorine or with halogen, you know halogen are group 17 elements or group 7 elements. Okay, like chlorine, fluorine will form would form a salt. Okay, that is group 1 metals. And when they react with water, will form a base. Okay, either base with OH group or base with oxide. All right. So winners, I'm still waiting for your aluminium. Winner left. Okay. Did you get the assignment I sent? Melody, yes, I also remember. You are not in the platform. Is it? Melody, I said you didn't register for chemistry. I didn't see you in the platform. So I sent assignments from the last class and I did not
Okay,
see
ma'am.
you to say that you attended the class. So even today's attendance, I don't know how to impute your name there. So I don't know. You find a way to be part of the chemistry class in the platform so that you see the things I'm uploading there. Okay.
Okay, ma'am.
So if do you
Yes,
have
ma'am.
any questions so far concerning today's class?
No, ma'am. Ma'am, please, how can I access the platform? The chemistry platform.
Okay, I'm going to get back to Mr. Lothar concerning you. Then maybe he will
Okay.
get back to you. I don't know how they would do it, but I will let them know.
Okay, ma'am. Thank you, ma'am.
Then winner. Okay, she's no longer here. Okay, I think that's all we have for today. If you have any question, you can actually ask, or if you have a suggestion for the class, for a subsequent class, you can also make the suggestion. Since you and winners, you're usually the people I see in this class. So we're going to be making the class to favor you both.
Thank you, ma'am.
Okay, so to summarize what we have done today, we talked about the periodic table and how we went from the first origin of the periodic table to the modern one that we have now, where we have the periodic table arranged in increasing atomic number. Okay, and the modern periodic table was introduced to us by Henry Hosley. Okay, we know Mendeleev very well, right? But Mendeleev Dimitri Mendeleev is not the um, founder or the person that gave us our modern periodic table. Okay, so Dimitri is the one we know as the father of periodic table, but he was not the one that gave us the most recent periodic table we are using. Okay, and we say every member of each group have the same properties, chemical properties. Okay, and we also said so they will now act the same way. Okay, and we'll talk about the trends in the periodic table in terms of atomic size, in terms of um, um, electronegativity, electron affinity, um, atomic radii charge, and things like that. We also talk about electronic configuration using the shell method and the Albach method. Okay, we said the shell method is very good, but it's good just mostly for the first 20 elements. Not as if we can't use it for more elements more than that, but it's more reliable for the first 20 elements. Okay, and we also talked about reactions of alkali metals, which are group 1. Group 2 are called alkali earth metals, while group 7 also have their names. Okay, it is group 7 in the simple periodic table where we have just the first 20 elements. But in the periodic table of more than the first 20 elements, the complete periodic table, it is group 17. Okay, those are called halogens. And then group 18 or group 0 are called the noble gases. Okay, these are some groups that have special names. Then we also have the lactanides and actinides, the ones at the bottom. So we mostly talked about and we said group 1 and 2 are the S block. So when you're writing the electronic configuration, it usually ends in a S, either 1S, 2S, 3S, or anything S. But when you're writing your electronic configuration and it doesn't end with a S, and you are dealing with group 1 and 2 element, that means that your configuration is not correct. Okay, then okay, that is pretty much what we did today. So that is for Melody and Winner. So Winner, I hope you didn't dodge giving us aluminium today because you did not understand. Did you understand what we did? And Winner. Okay, she said her network is bad. All right, that means in the next class, you will tell us about the aluminium configuration and you will also explain to us how you got it. So you have like more time to give us a perfect answer. All right, that's all we have for today. Bye-bye.
Bye.